So last time we were talking about, obviously, the last little bit of organic. We got into really nitrogen containing organic guys, such as these guys. Something to write with here. And we talked about, first off, amines here. And amines are basically those nitrogen containing groups. So amines, if I can spell right, try that again. Amines, there we go. They basically have that kind of derivative of ammonia. So they have a nitrogen and hydrogen sort of group, again, kind of based off of ammonia. We could classify these as primary, secondary, and tertiary amines based on, how many carbons are attached actually to the nitrogen in these cases. Primary would have one carbon attached to nitrogen, secondary would have two carbons attached to nitrogen, and a tertiary would have three carbons attached to nitrogen. We talked about naming amines, and we're going to go with the more sort of common name for amines, not really the official sort of type of amine naming, the IUPAC name. And here we basically just go to the nitrogen at sort of our center point, and we kind of look and see what type of carbon group there is attached to it. That's a 3-carbon group, which is a propyl, and then we basically put amine at the end of it. So this would be a propylamine. This is a primary amine. Again, 1 carbon attached to the nitrogen. We also looked at this guy as well, I believe. And here again, we would kind of do the same approach, look at our nitrogen, really try to figure out what groups we got going on there. This is 2 methyl groups, which means this is going to be a dimethyl. On the other side there, we have a ethyl group, just like we do, not just like we do over there, but we have an ethyl group. And again, we put it in alphabetical order. This would be ethyl, dimethyl, remember, ignoring the prefix D, and amine here. This would be a tertiary amine. It's got those 3 carbons basically attached to it. Any questions on that there? Okay, so let's talk then about some other amines here. So we do have aromatic amines, such as these. These guys will have basically a benzene ring. So remember, that's the benzene ring there with our obviously circle in the middle. This guy, I think we saw when we talked about benzene, this guy that has this NH2 group on it does have an historical name that's known as aniline. And again, that is sort of a name that is commonly still used today. And so when you see that combination like here, that would be aniline, which is where that part of it is. This obviously would be carbon number 1, as it shows there, 2, 3, and 4 coming around the corner there for 4-bromol aniline. We sometimes, as I might have mentioned before as well, is sometimes with secondary or kind of tertiary amines, we sometimes use that prefix of N. And that N indicates that group is basically attached to the nitrogen here. So this whole thing here is sort of aniline. But this methyl group, again, is not attached to a carbon where we normally would use numbers. So that's what the N stands for here, that group is attached to the nitrogen. So that's also a very common sort of way sometimes you'll see with amines. You'll see, like I might have wrote it, I think last time as well, instead of like, 3 something dimethyl, it may say something like N dimethyl or N methyl aniline. And again, it works kind of the same way as how the carbons are, except that we usually reserve numbers for carbons. So here we just use the N to indicate that group is attached to the nitrogen. Any questions on that there? So if we take a look at a couple of these guys here, and some look very kind of familiar, we again would want to go to our nitrogen and really figure out the groups that are attached. So that is a methyl group. If we come over here, that is an ethyl group. And over here is also an ethyl group that is there. So we basically got a diethyl and we have a methyl. So putting those together would be diethyl, methyl, and amine at the end of it. Now, over here, again, we have basically our aniline, which is right here, as we just talked about. And again, here we do have this ethyl group that's hanging off of it. And we could say an ethyl aniline. Again, the group here is attached to the nitrogen. And again, it's sometimes commonly done that way. This would be a secondary amine. Again, carbon right there and carbon right there. This guy would be a tertiary amine. And again, just to sort of give you the more IUPAC way of naming as well, as we talked about with those N's, you could also use the N for this guy here, and this would be N-ethyl and methyl methane amine would be the sort of IUPAC name. So you can see, again, sometimes they will incorporate the N's in there. For us, though, you could roll with the common name is perfectly fine. You could use the N in a benzene situation like this, or an aniline sort of situation like that. That would be okay. Any questions on that there? So we can also obviously draw line structures for these guys as well. You know, it kind of works the same way as when we draw it for carbon-based guys. Here's obviously, again, counting our carbons, 1, 2, 3 carbons. Again, only one carbon attached to the nitrogen, which is why this is a primary. And again, 1, 2, 3 carbons is the propyl group. And again, the amine at the end of it. Here, looking on this way, is 1 carbon, 2 carbons on that side. On the other side, 1 carbon, 2 carbons, 3 carbons. So that is an ethyl group, right? And that is a propyl group. And again, we just put the amine here. This is a secondary amine because there's a carbon there and a carbon there. And again, there are 2 carbons attached to that nitrogen. So when we're sort of classifying our amines, we want to look to the nitrogen and again, figure out how many are actually attached there. Carbons are actually attached to it. Now, amines, because they are sort of derivatives of ammonia, and ammonia is a polar molecule, and it does have that hydrogen involved, or that nitrogen and hydrogen. It has the ability to really form hydrogen bonds. Remember, what you need for hydrogen bonding is a bond between hydrogen, nitrogen, oxygen, fluorine. So here with amines, we have a bond between nitrogen and hydrogen. That creates that nitrogen-hydrogen bond where the hydrogen is more positive. The nitrogen is actually more negative in this case. And that does give it the ability here to do a little bit of hydrogen bonding sort of happening, you know, with water. That means that it is going to allow water to be fairly soluble, not water, to be amines fairly soluble in water for our primary and secondary amines. Our tertiary amines are sort of out of luck in terms of sort of interacting with water. And that's because, again, a tertiary amine would basically have 3 carbons attached. It's missing, obviously, the hydrogen that would be needed to sort of make a hydrogen bond. So our tertiary amines, they really can't participate there in hydrogen bonding because they sort of lack that hydrogen that's necessary on the nitrogen there. But our secondary amines, like this guy, has a hydrogen and a nitrogen bond, so it can hydrogen bond. And our primary amines, which obviously has this guy, which has a couple of these hydrogens here, can definitely hydrogen bond. So primary, secondary have the ability to do that because it does contain that nitrogen-hydrogen bond. Tertiary, no deal on that. It cannot do that because it has no hydrogen there to participate in that hydrogen bonding. So primary and secondary ions fairly soluble in water. Again, like anything else in organic, if you build out a lot of those carbon groups, it does sort of decrease the solubility. But 6 or fewer carbons that are attached there, fairly soluble in water. Any questions on that there? So again, this is what we just basically talked about, having that ability here with those hydrogens in our primary and secondary, but again, our tertiary lacking those guys. So like alcohols, the smaller the amines, including the tertiary ones, are soluble because they form hydrogen bonds with water. But, like most organic things, that 5 to 6 carbon chain, if you get above that, you're just, as we talked about a number of times, adding a lot of non-polar to that molecule, also making it very much bigger, which decreases its ability to really sort of hydrogen bond with water and would decrease the solubility of it in water. So when we get above that, again, you're just really decreasing that because you're just building up these guys that are really sort of non-polar. You got non-polar, and this guy, which is a tertiary, really can't hydrogen bond anyways. But you are creating a lot of sort of things that are getting in the way. Even if you did have a hydrogen there, the bigger the molecule get, as we talked about a couple of times throughout this organic, sometimes you get what is referred to as steric hindrance, which is a fancy way of saying things get in the way of water being able to basically interact with other guys. So here, which of the following we would expect to be sort of soluble in water? In this case, this is a primary amine. It has less than 6 carbons attached, so we would expect this guy to be soluble in water. This is a secondary amine, also has less than sort of 6 carbons attached, kind of 2 small groups attached. We would allow it or expect it to be soluble in water. Again, they both are containing these hydrogens that could hydrogen bond. This is not an amine. This is actually an alkane here. No nitrogen there or anything like that. Alkane is pretty much non-polar all the way through. As we talked about with our alkanes, we would not expect that guy to be soluble in water because he's going to try to be using, obviously, the dispersion forces while water is trying to use the hydrogen bonding. So out of these two, A and B should be soluble in water. C, not so much soluble in water. Any questions on that? And that really is sort of a common theme with organic guys, is that ability of them to be soluble in water really revolves around a lot of times that hydrogen bonding ability. So, if you have those organic guys that have the ability to hydrogen bond, they usually are soluble in water, and they also usually have a larger melting point, boiling point because of that ability to hydrogen bond. Now, let's talk about a couple reactions that amines do undergo. Since amines are really, again, that derivative of ammonia, ammonia is a weak base, which means they really, base spelled with an E probably, there we go. They basically do behave really like a base, so it's going to accept an H+, and that's how we get NH4+ and OH-. Same sort of thing happens here with our methylamine, for example. It's going to basically pick up that H+, that Bronsted-Lowry definition, basically, of donating that H+. Basically, all we did there is put an H+ onto our methylamine. We don't have to worry about the naming part of this salt. But more importantly, what really makes these guys really more basic is you can see you get this production of hydroxide, which is pretty much what a base is, the definition of a base. So amines, they really do sort of behave in water, basically, just like a weak base. We're not going to worry about the amine salts there, which also means that they will basically do also like a neutralization reaction with something like HCl, right? If we reacted with hydrochloric acid, same thing's going to happen. We're going to donate the H plus over. You could just count up the hydrogens. We added a hydrogen and a plus, and when the hydrogen comes off here, we're left with Cl minus. So again, it pretty much makes a salt here when it reacts with an acid. Same thing will happen over here. Again, that H is going to come right on over, that H plus. And again, we make these kind of amine salts are formed in this particular case. So you could think of amines really as bases, as proton acceptors, just like in sort of what we talked about in acid and base chemistry. Works the same way, except that you don't really get like a salt and water in this case. You just kind of get a salt in this case. So these are really equivalent to just the salt, which is ionic compound, hence the positive and negative charges that we see here. Any questions on that? We're not going to worry about the properties of ammonium salts, so we're just going to kind of look at them really quick, but you're not necessarily responsible for any of those sort of things. But some of these things are used in ingredients, these sort of salts in medicine like Benadryl and so forth, as you can see here. Also, they are sort of derivatives for narcotics like cocaine and so forth. You can see our amines sort of happening. And they're sometimes referred to as alkaloids. Alkaloids are physiologically active compounds that contain basically nitrogens. They're used in some different areas like antidepressants, stimulants, and so forth. This is nicotine. And again, you can kind of see here, again, we have an amine, right? Our sort of nitrogen containing group there that's involved. Also caffeine as well. So if we look over here, again, we have our sort of group here, our nitrogen containing groups that are there, and obviously found in caffeine. Morphine as well. Here again, you can kind of see our amine aspect of it, and codeine and morphine that are found here, used for painkillers. All right. So let's take a look at these guys, and you obviously don't need to draw any of those other things, obviously, that we just talked about there. We want to draw these guys here, which is methylpropyl amine. And you really can sort of start it like normal. You could start with the N. And remember, methyl is a 1-carbon group. Propyl is a 3-carbon group. And we could just fill it in like normal with our hydrogens. And the other thing is, this is a secondary amine, which means it also should have a hydrogen there to give it sort of 3 bonds, just like ammonia sort of. And that would be a secondary amine. 2-chloroaniline, aniline being our kind of NH2 guy, that is our benzene ring. This is 1 and 2, we would put a chloral. And you may be asking yourself or asking, why is it not this? This is not this guy because this chlorine is attached to the nitrogen here. And if it said N-chloral, then that would be the one. But here it actually has a number, which implies it's attached to a carbon. That's part of the chain. So again, that's sort of the difference between there where we saw those N's sort of in play. Any questions on amines? So amines, obviously, you do need to know the functional group. You need to know how to classify amines like we talked about. You need to know how to name amines in sort of the common way of naming, like we see here in A, methylpropyl amine. You need to know aniline, which is still part of the benzene sort of guy. And you need to know, again, that basically amines basically do act as a base as they react with water or as they react with an acid. Any question on those? Okay. So the last organic group we're going to talk about are amides, and amides are kind of like amines, except that it has sort of a this sort of group attached, almost like a carboxylic acid with an amine sort of onto it. So that is the functional group of an amide, sort of that carbon oxygen double bond into like an amine almost here as well. And you can see Tylenol here, which is an aspirin substitute. Here's sort of that amine aspect of it, right, or amide aspect of it right there, which is acetaminophen. So amines, like I said, basically are very similar to carboxylic acids, except instead of attaching with that OH there, we basically put an amine group in place of it, and that gives us our amides. So you definitely need to know the functional group here of an amide, which is, again, what I just drew, carbon-oxygen double bond with our NH2 happening there. How do we get an amide? Well, you might imagine, since it kind of looks like a carboxylic acid, the way that we get an amide is to take a carboxylic acid like this guy and take something like ammonia or an amine, right? And basically put them together. And what do we take out? Well, we take out water, H2O. And then everything else stays the same, CH3, CH3, CH2, CH2, carbon oxygen double bond, carbon oxygen double bond, NH, NH, and H. And H. Again, same thing here, take out water when we react it with an amine. And again, just basically squish together everybody on the other side. So again, that reaction, pretty straightforward. Water goes out, squish everybody together, and you're good to go in terms of your amide. And that's why, again, it really does look like a carboxylic acid with an amine on it, or an ammonia sort of on it. And that's basically where it comes from. Any questions on that there? So here, if we did this, you could see same thing's going to happen if we just sort of rearrange this guy, kind of turn him around a little bit. I'm just going to redraw the guy there on the bottom, just kind of flip him around. We get our H2O coming out. And then we basically just stick everything together. This entire thing here is the same as the entire thing that's over here. And if we count, we have a nitrogen and a hydrogen, and CH3, CH3. Again, basically, like everything else in organic, there's just one spot where all the action occurs, and you squish it together. Nothing weird happens, like the thing opens up or anything like that. You know, you just basically put it together. Any questions on that reaction? And again, this is a carboxylic acid. And this is a primary amine here. So those guys going to give you your amide with some heat. The heat basically does the dehydration part, takes out the water, basically. Any questions on that? Okay, then going into our amides here in terms of naming. Who cares? All right, we're not going to name them, so we're still not naming them. Still not naming them. Still not naming them. Still refusing to name here. There we go. In case you haven't picked it up yet, you don't have to name them. So you don't have to worry about naming amides, but you do need to know the functional group of an amide. You need to be able to recognize it. You do need to know that reaction we just saw there, how an amide is formed. But again, no naming is necessary here. Here are, again, just some amides and stuff like that. Urea, you could kind of see your amide here. Also, some barbiturates here. You could also see your amide that's sort of happening here. This is our carbon-oxygen double bond with our NH on it there, which is our amide sort of part of it. Aspirin as well. And again, happening right here, carbon-oxygen double bond and line structure. There's our amide as we look at it. So we do need to talk though about these two reactions that amides undergo, and these are hydrolysis reactions. And we saw some hydrolysis reactions when we were talking about carboxylic acid, so it sort of makes sense here. In an acid hydrolysis, we produced a carboxylic acid and the ammonium salt. In a base hydrolysis, we produce the salt of the carboxylic acid and we end up with an amine or ammonia. So down here, this is the acid one. And again, we're going to break it right there. And in the acid one, the good way to remember that is if you do the acid hydrolysis, you get back the completed carboxylic acid. So we get back the completed carboxylic acid. This is going to come back. We're going to put the OH on there. And what we're left with, though, is we do end up with a salt that's left over. We put a hydrogen back onto here when that nitrogen part comes off, and we got that NH plus, 3 plus, and H4 plus, and Cl minus here. So we got the carboxylic acid back, and we get a salt that's coming back. In the base hydrolysis, we produce the salt of the carboxylic acid, but we do get ammonia back. Again, going to break it right here like before. We are going to kind of put our H back on here. And we get really the amine back together in this case, and the carboxylic acid doesn't come back together. So if you remember, we talked about the amine and ammonia as being bases, weak bases. So if you do something that's a base hydrolysis, which means you involve basically a strong base like sodium hydroxide, you should remember that you get these guys back completed. If you do something that involves an acid, like HCl there, we get back, again, the acid that's complete. So that's a good way you can kind of remember, what you get at the end of it. It's by sort of what's happening. Is it the acid or is it the base? As to sort of what gets sort of brought back completed. So let's take a look at this one here. This is the base hydrolysis of this amide. So remember, in the base hydrolysis, we're going to get back the completed base, which in this case is the amine. And that means that when we go through separating these guys out, to the right, we will get this guy back completed. As you can see, the H comes on, but we do not get the carboxylic acid completed. That becomes a salt. So again, that's the way you kind of want to remember what's happening there in those reactions there. Any questions on that reaction there? So again, if you had something like this, and you did this with water with like an acid as a catalyst, again, when we're doing the acid, we would expect to get back the completed carboxylic acid by putting our CH3, CH2, CH2, C double bond O, OH, and we would not get this guy to be completed back. We would get something like, it's got to be plus, and maybe it was HCl. We would have a minus, so we'll get back the salt. So acid hydrolysis gets us back the carboxylic acid in this reaction with the amide, and the base hydrolysis gets us back the base component of the amide, which is the amine. Any questions on that there? Okay. So since you don't have to worry about naming amides, you obviously don't have to worry about drawing amides, but you do need to know, again, the functional group of it, which again, if we look at these two guys here, functional group of the amide is right there, and on this guy here, right about there. All right, so in terms of amides, just to be clear on what you need to know, amide functional group, you need to know the preparation of it, the reaction, acid, base hydrolysis reaction. no naming, or drawing of amides. Any questions on any of that there? With that, that actually does wrap up chapter 14 and the last organic chapter that we're going to talk about. Any questions on that before we roll into carbohydrates? All right, so we're then going to roll into carbohydrates. That's just also from your book there of some of the selections. Carbohydrates will be the last lecture that we will sort of talk about here live. I posted up the other day the lecture for chapter, and by the way, this is wrong. This is actually chapter 13 nowadays in that book. Switch chapters. We just did 14, so there's no misunderstanding. It's chapter 13 in the new edition of the book. I posted up lecture for chapter 15 and 16, one lecture for both of those chapters. And as I mentioned in the video, whatever is in those lectures, you're responsible for. And we're not going to obviously talk about everything in those chapters. So whatever was covered in those is what you need to know. It's only an hour long, I think, for both chapters. So not too bad in terms of the information that's there. So we're going to talk about chapter 13 actually in this book, and it is carbohydrates, so bread, pasta, all that good stuff. So we're going to start with what a chiral molecule is and sort of what chiral sort of means. When we talk about chiral molecules, they basically have the same number of atoms, but they're arranged differently in sort of three-dimensional space. In order for something to sort of be chiral, the carbon atom needs to be attached to 4 different groups. So if you're looking at something which is very common in carbohydrates, carbohydrates basically are guys that have carbons, hydrogens, and oxygens as carbohydrates. And when you look at those guys, sometimes you look at the carbon and try to determine, is this thing what is referred to as a chiral carbon? And what that means is when you look at that carbon, it should have 4 different groups attached to it. Now, they are mirror images that do not superimpose. So what that means is if something is chiral, if you take the mirror image, it will not superimpose on each other. And you might be wondering, you know, why do we see the hands there? So the hands is a very common sort of example of that, which means when you put your hand, for example, up against the mirror, what you see sort of staring back at your hand is your other hand, basically, right? So if you put your hand up, you see your other hand. Now, if you take the hand out of the mirror image out of it, and if you do some rotation of it, if you move it around, there is no way possible that you could get the hand that was the mirror image to fit perfectly on the original hand. You may say, well, yeah, they kind of fit. But if you think about it, if you take your mirror image out and you put them right on top of each other, your thumbs do line up, but one is palm up and one is palm down, which means they're not exactly the same. If you do some weird rotation, you could get palm up and palm down, but your thumbs are on opposite sides, so they don't really match up correctly either. So when we say something is a chiral molecule, what it means is, for example, if we like push that molecule up against a mirror and we take the mirror image of it out of it, it will not, no matter how much you rotate or move it around, you will not be able to get it to sit perfectly on the original substance. And that's what basically chiral means. Any questions on that? And again, you could do that with your hands. Be careful, don't hurt yourself trying to rotate your hands. But again, you can move it around. You'll never get everything to perfectly line up perfectly the same. Now, mirror images, chiral compounds cannot be superimposed. The 2 compounds really don't align. So again, if we look at this guy, first off, we know this is a chiral compound. That is carbon in the center. It has a hydrogen, which is different than a chlorine, which is different than an iodine, which is different than a bromine. That is 4 different groups attached to the carbon, and that would make this a chiral molecule. That would make that carbon what is referred to as a chiral carbon. When you put that up against the mirror, they reflect, right? This guy reflects here, this guy reflects here, this guy and the guy in the back kind of reflects to the back. If you take that mirror image out, like they kind of show over here, you could do a bunch of rotation and you may get a couple of things that match up. So you can see, you could get the hydrogen and the iodines to sort of match up. But even with rotation, you're never going to be able to get all 4 of these groups to perfectly match up. There's going to be something that is not going to be in sort of the right orientation, and that's what chiral means. Now, if you happen to have a molecule where you do take the mirror image of it and it does superimpose, that is what is referred to as being achiral. So an achiral molecule is one where, again, if you look at the carbon in the center, we have a hydrogen that's different than a chlorine. We have a bromine that's different than those two. But here, we have 2 guys that are the same group attached. So because of that, that is achiral. If we do our mirror image here and we take our mirror image, in this case, we can rotate this molecule enough that it will sit perfectly on top of the original molecule. As you can see here, right, we don't see 2 kind of separate molecules. They were able to be rotated enough that they fit perfect on top of each other, and that would be an achiral situation. Mirror images perfectly match each other when you put it in there. So chiral compound, and especially a chiral carbon, needs 6 different groups, 4 different groups attached to that carbon. Mirror image does not superimpose. Achiral is one where you don't have 4 different groups attached to the carbon, and the mirror image will superimpose on each other. Any questions on that there? Here are some everyday sort of chiral and achiral. Chiral like our gloves there, like our hands. Achiral like the soccer ball. Our shoes as well. Again, something's not going to be right when you mirror image it and get it to sort of match. And right-handed scissors. I'm not sure what left-handed scissors would be then in that case. So let's take a second here and try to determine, is each of these chiral or achiral? So take a second and see what you come up with. Okay, so let's take a look here. So first off, in this case, we want to look at kind of the center carbon, if you will. We see a chlorine, which is different than a hydrogen. That's different than a methyl group. And this here is a ethyl group. So that is basically 4 different groups that are attached to that carbon. That would make this guy a chiral molecule. Any questions on that there? Looking over here at this carbon, we have a chlorine that's different than a CH3, different than a hydrogen, but here we run into a little bit of a problem. We actually do have 2 groups that are the same in this case. That means that this guy would be considered achiral. Again, you need 4 different groups there for it to be considered chiral. Looking at our last guy here in the carbon, we got a methyl group that's different than a chlorine, that's different than a hydrogen, and that is different than a bromine. So that is 4 different groups. That would make this a chiral molecule. Any questions on how you determine that there? Now, in terms of mirror images, we would expect this guy to not superimpose the mirror image. We would expect this guy to superimpose, okay, the mirror image. And we expect this guy, like the first one, not to superimpose the mirror image. Any question on any of those 3 there? So sometimes we represent carbohydrates and so forth using what is sometimes referred to as sort of Fisher projections. Spit that out. And it's sort of a 2-dimensional representation of a 3D molecule. We place the most oxidized group up on top. We use vertical lines in place of dashes for bonds that go towards the back. We also use horizontal lines in places of wedges for guys that come forward. So normally, when you draw something sort of in 3-dimension, you kind of do the dash line to represent that group is going back. You kind of do the wedge group to represent that guy is coming forward or out of the paper, if you will. So here we use sort of horizontal lines and vertical lines to kind of represent that 3D sort of structure. And just to give you a look at what that looks like, here we go. We have our vertical lines and our horizontal lines. And also important, kind of like in organic chemistry, pretty much where any lines sort of intersect each other, if you will, it's assumed that that is a carbon. Obviously, if there's nothing else written there, those would be carbons. So if you have something like this, for example, that would be a carbon, carbon, carbon. And a lot of times we'll have like this sort of group maybe up on top and maybe something like this on the bottom, and some H's and some OH's and in our carbohydrates. So that's again a very similar one. And most of the time when we draw carbohydrates, we usually don't include the carbons here. Again, it's just sort of written sort of like a straight line and kind of like line structure in organic chemistry. Any questions on that there? Also in carbohydrates, we oftentimes can classify these guys as D or L. And what does that mean, D or L? Well, basically D means right. L means left, basically. And what are we talking about? We're talking about left or right. The last OH group on the last chiral carbon. So first off, we actually do start numbering most of the time in carbohydrates based off of this group up here. There's usually some type of group that has a carbon-oxygen double bond happening, that carbonyl group. And that is usually carbon number 1. By the way, this intersection here is carbon number 2. And this guy down here would be carbon number 3, counting downward. Now, when we look at this, we're looking to try to determine chiral carbons. So first off, if we look at this guy, that is attached to one group, 2 groups, and this entire bottom part is a group. That's only 3 groups, right? So for something to be chiral, you need 4 groups attached. So that guy is definitely not a chiral carbon. Now, if we look at the carbon number 3 there that I highlighted, this carbon has an OH group attached. It has everything above attached, but it has 2 hydrogens attached. So it has 2 of the same, which means that carbon is actually a chiral. And just to blow up that carbon so you can see what I'm talking about, if we just draw that last sort of bond, I'll just put R. R would represent everything above that carbon, number 3. It has an OH group attached, and it has H and H attached. So again, the presence of both of those things mean that the carbon number 3 is not chiral. Now, when we look at carbon number 2 there, it is chiral, as you can see by the big arrow that says chiral. But why it is chiral? Because this whole entire thing is one group. This guy is another group, which is different. This hydrogen is considered a group in this case, which is different than the other 3. And this entire thing here is considered a group, which is obviously different than the other 3 things. That meets our definition of chiral, right? Is 4 different groups attached. This is our last chiral carbon from the carbon-oxygen double bond going down, which means when we look at it, we see the OH group here is on the left. And that means that this is L-glycerolaldehyde. Necessarily, the name is not important right now, but the L location. Any questions on that there? Basically, it's the same exact guy over here on the right, looking at this chiral carbon, which is right here. Again, one group attached, two groups attached, three groups attached, and four groups attached, making that guy the chiral carbon. We see here that our OH group is on the right, which makes it D-glyceraldehyde in this particular case. Any questions on that there? So when determining D or L, we're always looking the last chiral carbon that you have, going from the carbon-oxygen double bond and sort of away from it down in a lot of cases. All right, so why don't you take a second to determine whether each of these, whether each pair is a mirror image that cannot be superimposed. That's like a double negative there. So why don't you determine whether or not they cannot be superimposed. You know, you could kind of imagine, by the way, in each of these cases that there's kind of like a mirror that's sitting right here, and they're sort of reflecting in each other. Easiest thing maybe to do is to first figure out, are you dealing with a chiral molecule or not? So if we look at this, I got this group right here, which is different than this group, which is different than this group, and different than that group. That is 4 different groups that are attached, which means that carbon is chiral, which means when we take our mirror image here, it is going to be non-superimposable. So these guys would not be superimposable based on the question. That means yes is the correct answer to the question. If we come down here again, you could kind of think of this as your mirror happening here. It gets reflected. And again, if we look at this carbon, we see 2 hydrogens that are attached, which means it does not have 4 different groups. And we would expect this guy to be achiral. We would also expect this mirror image to be superimposable in that case. Any questions on that? So in terms of the actual question, it actually wanted to know, again, it was kind of worded weird. It wants to know which of each of these paired mirror images cannot be superimposed. So if you ever look at the answer, this is why it says yes to this guy and no to this guy. Yes, this one cannot be superimposed. No, this one cannot be superimposed. So it's kind of like a weirdly worded question. Any questions though on that one there? Okay. So let's then talk about carbohydrates a little bit more. Carbohydrates obviously is a main source of energy from our diet, right? We take carbohydrates, goes through glycolysis. We use it for energy. We store excess of it, right? So later it could go for gluconeogenesis, break back down and be used for sort of energy and so forth. There's a Krebs cycle in there as well. I think it's been a while, but that's what I remember. It is basically composed of those 3 elements, carbons, hydrogen, and oxygens. They're also sometimes called saccharides, which basically means sugars. So we talk about the carbohydrates sometimes as being sugars. And there's our 3 starchy guys there, our bread or our potatoes, and looks like some pasta happening there. How do we sort of produce carbohydrates and so forth? They are produced by photosynthesis in plants. Basically, there's a couple of reactions in photosynthesis. There's a light reaction, which involves some electrons being transported, creates some energy, which goes into the carbon fixation cycle, CO2 coming in from air, and this whole sort of process of sort of respiration where we create carbohydrates through respiration, again, kind of breaking it back down to CO2. And again, that light initiating a lot of the reactions and producing the products that are needed to kind of produce those carbohydrates and so far in the cell. There are a few different types of carbohydrates that we're going to talk about. And as we go through this chapter, we'll kind of focus in on some of these a little bit more than maybe some others. But one thing that we'll kind of talk about are some monosaccharides. Mono, like the name implies, mono meaning one, so one sort of sugar molecule. There are also disaccharides, di meaning two sugar guys together. And there are polysaccharides, which means a lot of sugar molecules are basically held together. That's a monosaccharide, just one sugar molecule, disaccharide, and lots of them together. You can see water is involved, which means if we want to break these apart into their individual guys, we basically just add a water for each one. And when we do, we basically can break everybody apart into their monosaccharides. So water breaks them apart. And as you might imagine, when we put together, for example, for a disaccharide or a polysaccharide, we basically connect those two through removing water. Basically, we remove water, allows it a place basically to connect in. So let's start off with talking about monosaccharides. Monosaccharides consist typically of 3 to 6 carbons. They typically will have either a aldehyde group up on top or a ketone group up on top. And these guys are same guys that we talked about in organic chemistry. So a reminder, aldehyde group is this, right? Ketone is that sort of 3 carbon run with the carbon oxygen double bond. So how do these guys sort of look like in sort of a carbohydrate drawing? Well, they kind of look like this. Usually that aldehyde group or ketone groups towards the top. You have several sort of carbons that are interacting with each other. And then you have CH2OH or something on there. Again, if we were sort of counting, this would be carbon 1 right here at that intersection, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Now, a ketone is a little bit different because you need that 3 carbon run, just like you do in organic chemistry. So you'll have something kind of drawn like this. Maybe they'll write the carbon in, maybe they won't. And then you'll have something that looks like this. So again, you have basically that carbon, 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 3 carbon run for our ketone group, just like in organic chemistry. So like right there, ketone. And obviously our aldehyde group here at the end, just like it is in organic because of that hydrogen that's present. So those are 2 very common ways. Our carbohydrates are basically displayed. Obviously, some will have some OH groups and some hydrogen groups sort of happening, along the way. And these are the kind of the other things that fill it in when we look at these guys. So let's talk about these different sort of groups, these sort of organic groups, if you will. The ones that have the aldehyde group up on top, this aldehyde group is what is sometimes referred to as an aldose. An aldose is a monosaccharide, so one sugar molecule that basically has that organic aldehyde group up on top. So here you can see your aldehyde group, make it an aldose. We also can determine sort of how many carbons there are and classify the carbohydrate based off of how many carbons there happens to be. If there's 3 carbons, it's sometimes referred to as a triose. If there's 4 carbons, it's a tetrose, like tetra. 5 carbons, pentose, and hexose would be 6 carbons. So here, if we look at this 1, 2, 3, and 4 carbons there, now 4 carbons would make this a tetrose. That's why it's sometimes referred to as an aldotetrose, because it's an aldose with 4 carbons that are present. So if we also look at this guy, we could relate what we talked about a second ago. This is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4. First off, take a second and determine how many chiral carbons are there. And is this L or D? So take a second and see what you come up with, and we'll talk about it. Chiral. Carbon number 2 has got a hydrogen. It's got an OH group. It has everybody coming downward as a group, which is different than everybody coming upwards as a group. So those are your 4 groups, and they are all different from each other, which means chiral carbon number 2 is chiral in this particular case. Any questions on that there? Now, if we look at this, and get rid of all my scribble here, we look at carbon number 3. What do we got going on with carbon number 3? With carbon number 3, we have a hydrogen that's different than an OH. Again, coming downward is also different than those two. And now everything that comes above the carbon number 3 is considered one group. And that is obviously different than the group below it, which means carbon number 3 here is also going to be chiral in that case. Any questions on that? What about carbon number 4 there in this particular case? So if we look at carbon number 4, we have those 2 hydrogens that maybe you can see right off the bat. And as these 2 hydrogens, kind of like what I drew out a second ago, you got this situation sort of occurring along with everything else. So those 2 hydrogens are going to make it achiral in this case. So there are actually 2 chiral carbons in this carbohydrate, and you can't have more than 1 chiral carbon in a carbohydrate. You can also have some achiral carbons like we have as well. So what we're looking for in terms of determining L or D is we want to find the last chiral carbon from carbon number 1. The last chiral carbon in this case is carbon number 3. At carbon number 3, my OH group is on the right. Because my OH group is on the right, I am looking at a D carbohydrate here. Any questions on any part of that? Okay. So these are aldoses, basically has the organic functional group of the aldehyde that's involved. And obviously we have, as we saw before, the ketone group involved, and those are what are referred to as ketoses. And ketoses, just like sort of aldoses, basically have that organic group, that carbon, carbon with the double bonded oxygen group involved. So it does have obviously that ketone group here. And again, that's that 3 runs of carbon. And much like in organic chemistry, if you remember, our aldehyde group is always at the end, like we saw here, right? Aldehyde group at the end. Our ketone group, if you remember from organic, can never be at the end. It has to be in the middle-ish, away from the end, because it needs that 3 carbon run, which is right here. So that's that 3 carbon run that we're looking for our ketone. We would number the same way. In this case, carbon number 1 would actually be this carbon. The carbon oxygen double bond would be carbon number 2, just like in organic chemistry, given it the smaller number. This would be 3, 4, 5, and 6. That means that this guy is a hexose. It's a ketose hexose or a ketohexose for ketose, and 6 carbons involved. In this particular case, there are a chiral carbon right here, a chiral carbon right here, and a chiral carbon right here. This first carbon is not chiral because of the 2 hydrogens. This guy only has 3 things attached, so he is not chiral. And this guy here also not going to be chiral because of the 2 hydrogens that are attached. So this guy actually has 3 different chiral carbons, number 3, number 4, and number 5. Again, if we're looking for L or D, we want to go the last chiral carbon from our carbon oxygen double bond, which in this case would be carbon number 5. We see the OH group there, it's on the right, which means this guy also would be considered a D. Any questions on any part of that there? So take a second here for each of these and determine Is it a keto or aldo? Is it tetros, pentos, or hexose in each of these cases? Kind of the easier thing to sort of tackle. And it's usually fairly obvious, as you can kind of see here. Again, knowing those organic guys, we could hopefully recognize that as an aldehyde group. And over here, we got a 1 carbon, 2 carbon, 3 carbon run with our double bond being second in there, which would be our ketose group or keto group. So this is an aldose because of the aldehyde group. This is going to be a ketose because of the ketone group that's present. What's left is just to count the carbon. So again, starting where that carbon oxygen double bond is going to be carbon 1. This would be carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6, which means this would be a hexose because it has 6 carbons. Starting here, again, this would be carbon 1 above the carbon oxygen double bond, carbon 2, carbon 3, carbon 4, and carbon 5. That would be a pentose. Any questions on that one there? All right, so let's talk a little bit about monosaccharides a little bit more and sort of their structure. As I mentioned before, a lot of times carbohydrates are drawn with these sort of no carbons labeled, almost like line structure. Again, we put the most oxidized group towards the top. And in the case of an aldose, that's going to be your aldehyde group. In the case of the ketose, that's going to be kind of your carbon 1 with the carbon oxygen bond being carbon number 2. We show sort of the chiral carbons as intersections of the vertical lines. So usually for the most part, by the way, when you're sort of determining like D or L, for example, usually right above this group, not 100% of the time, but right above that group is usually our last chiral carbon. So if we look at that group there, that's on the left, which is why this is L. Again, just kind of going one up from there. This guy is on the right, which is again why this guy is D in this particular case. As you can see here. I won't say 100% of the time, but usually, again, if you kind of go up from that last little group on the bottom there, that's usually the one that you want to kind of look at. Any questions on that there? All right, so if we look at a couple of these guys here, this is glucose. You do need to know glucose and sort of the structure that goes with it. You probably won't be asked to draw it, but if you see it, the drawing given to you, you do need to be able to recognize it as glucose. So you do need to be able to recognize this as glucose. This is an aldose because it has the aldehyde group there on top. It has 1 carbon there, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and 6 carbons there. It is a hexose. And the OH group here at our last chiral carbon on the right-hand side, which is why it is D. This particular guy has 1 chiral carbon, 2 chiral carbons, 3 chiral carbons, and 4 chiral carbons basically happening here. This is D-ribose, which you do need to know, biotic galactose as well. Put a little star on this slide. You do need to, again, be able to recognize the structures here. Again, not necessarily draw it, but if it was given to you, be able to recognize what it is. This is, again, an aldose because of the aldehyde group that's there. Also has 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5 carbons. Means this is a pentose. This guy right here being our last chiral carbon, OH group there on the right-hand side, giving us D-ribose in this case. And over here is galactose, which also, again, going to be an aldose. Has 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and 1 more makes 6, along with obviously that guy up there. That is a hexose. And again, the furthest chiral carbon from that guy is this guy right here. And we see the OH group there is on the left, which is why it is L-galactose. Any questions on that one there? So take a second here and decide, is this D or L for each of these? Okay, so again, we're always looking for the last chiral carbon from the carbon-oxygen double bond. And again, if you count it, this is chiral, that is chiral, and this guy right here would be chiral. That is the last one from the carbon-oxygen double bond. We see the OH group there is on the left, so we would expect this guy to be L. Same approach here, carbon-oxygen double bond. Last chiral carbon, that is a chiral carbon, that is a chiral carbon, which means this is our last chiral carbon really from the top there. And again, we see that our OH group there is on the left, so that would be L as well. This is the last chiral carbon here, in this case, 1, 2, 3 being here. Again, the last one actually from here, that is the carbon-oxygen double bond. This again is a ketose because of that ketone group. These first two are aldoses because of the aldehyde group that's present. Here we actually see the OH group being on the right-hand side, and that would be D, fructose in this case. Any questions on that one there? So let's talk a little bit more in depth here, a little bit about D-glucose. So as I mentioned before, again, you need to be able to recognize the structure of it if it's provided to you. It's found in fruits and corn syrup and honey. As we saw there just a second ago, it again is an aldose and a hexose, basically, because this is 6 carbons. C6H12O6 is also sort of known as blood sugar in the body. It is the monosaccharide in things like starch, cellulose, and glycogen, which we will talk about a little bit later on in this chapter as well. We sometimes do measure, obviously, our in the body, our sort of glucose levels, sort of normal range. And obviously, if you're not within that sort of normal range, you're too high, which is what hyper means, right? More than, as we sort of talked about previously in like the solutions chapter, hypo means less than, right? So a little lower of a glucose level in your body there. After several hours after sort of ingesting type of glucose. Remember, again, glucose being used as sort of energy in your body, and we then would typically store any excess to be used a little bit later on and broken back down as a source of sort of energy. Fructose, which again is another one that we talked about there, that you do need to recognize sort of the structure of it, and again, be able to know that it is fructose. It is the sweetest carbohydrate found in fruit, juice, and honey. In the body, it actually does convert into glucose. Again, it is a ketose. And again, we can see our ketone group there, right about there, which is obviously a major difference between glucose, which is an aldehyde type group up there. This is a D-fructose because of the last chiral carbon, which would be right there, has the OH group there on the right-hand side. And again, that means that it is D. Galactose, which was another one that you did need to sort of recognize. Also, again, you can see all these guys have really almost the same formula, except that the sort of arrangement of the OHs and stuff are different. It's obtained from lactose, a disaccharide. It's not found free in nature. It's very similar to glucose. Again, also an aldose, also a hexose in this particular case. But the exception is on carbon number 4, which would be 1, 2, 3, and 4. We have that OH group that not necessarily seen there in glucose, and that's a slight difference between those two. Any questions on that there? Okay. So we'll just look at fructose here since you don't have to draw it, but you do have to recognize it. And again, this is very similar to the way that it would be drawn here. And sometimes, like we saw previously, you may even see kind of no carbon drawn there and just like the oxygen sort of drawn like so. And again, that's a very common way as well that you see it. Again, these guys being our chiral carbons intersecting there at those points. This being our last chiral carbon, which again is why it's our D fructose in this case. Any questions on that? So then let's talk a little bit about cyclic structures of monosaccharides. And really, cyclic structures will have really one of two sort of shapes, if you will, or structures, if you will. And they will either be this sort of really 5 carbon chain. It's only 5 carbons because there's a oxygen in there, kind of like cyclohexane, but cyclohexane has 6 carbons, right? But this one again has that oxygen in there, so there's only 5. And it will sometimes have one that looks like a cyclopentane ring. That is not cyclopentane. Try that again. There we go. Which has 5 carbons, but this one actually only has 4 carbons. Again, 1 carbon there, 2, 3, 4, and 5. This guy having 1, 2, 3, and 4. So what ends up happening is the hydroxyl group at carbon number 5 reacts with the aldehyde or ketone group, and it basically forms a ring. And it basically forms a ring structure. So our sort of straight chain, if you will, sort of guys will kind of fold into a ring and out of a ring. And you might be wondering, you know, sort of how does that work? So let's just take a look at one just to kind of show you, you know, how you go about kind of doing this. And I'm just going to kind of clear some room here. So I got somewhere to draw. Let's say we had a carbohydrate such as this guy here. Kind of go down to and let's just call this one OH. We'll do H, OH, OH, and these guys would be H, OH, H, and H. Now, let's say we wanted to basically draw this guy into a ring structure, like it decides it's going to be a ring type structure. Now, how do we know how it all works? Well, and how do we know which one we should draw? Well, the first thing that's going to happen is basically this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4, this is carbon 5, this is carbon 6. So that last kind of chiral carbon will sort of come up and attack sort of where the carbon-oxygen double bond. How is that going to help you know sort of which ring you should draw? You literally could count the carbons. That is 1 carbon involved, 2 carbons involved, 3 carbons involved, 4 carbons involved, and 5 carbons involved. There's actually 5 carbons involved. And what that tells you is you should start out with this ring. So you literally can just draw that ring just like that off the bat. Again, by just counting how many carbons are involved. So you may be wondering, like, where do I put everybody, right? So what always happens, as you can see here, is this group right here, for example, at carbon number 6, is not part of the ring. So the ring is going to be everything that basically just closed in inside that little arrow that I made. So that guy right there is not going to be part of the ring. So this guy here will always end up at this carbon coming up CH2OH. And it's always to the left of that oxygen is where that guy will end up. And that is carbon number 6, if you remember from our numbering, which means if we follow down, this would be carbon 5 going counterclockwise. That would be carbon 4, carbon 3, carbon 2, and carbon 1. So we could count up how many carbons are involved, draw the appropriate ring. This carbon number 6 always ends up above the ring to the left of the oxygen. And then we could go down and counterclockwise number all the carbons. Any questions on that so far? All right, so how do we know where to put everybody else? The next thing you really want to do is just take this thing and basically just drop it on its side. And what that means is I'm just going to drop it straight down. And when I do that, again, we still end up with that carbon number 6 here. So this is carbon 1, this is carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. I just took the thing and dropped it down. When I look at that, everybody that's on the right-hand side will end up down, right? So on the right-hand side, I have an OH, I have an H, I have an OH, and I have an OH, right? So basically, as this thing is dropping down, everything on the right will end up down. Everything on the left-hand side will actually end up, like so. So again, took the thing, dropped it to a side. Everybody on the right goes down, everybody on the left goes up. And now we're ready to sort of build out the rest of our guy here. We always skip number 5 because 5 and 1 is basically what came together, right, to make that ring. So these guys came together to make that ring. So then we go to carbon number 4 and we see the OH group is down. So we go to our carbon number 4, draw a line and actually put the OH group down. We go to carbon number 3, we see the OH group is up. We go to carbon number 3, draw the line and put the OH group up. We go to carbon number 2, we see the OH group is down. We go to carbon number 2, we draw the OH group down. Any questions on how I figured that out there? So there is one issue that happens at the very end, and at the very end, it determines sort of what you do with the last OH group. The last OH group is determined by what anomer you're asked to draw. If you're asked to draw the alpha anomer, sometimes referred to, the last OH group goes down. If you're asked to draw the beta, the last OH group would go up, and they typically will ask you to draw alpha or beta. So why don't we just do alpha here? And that means that the last OH group we would draw down. If we wanted to do the beta, it would look exactly the same, except that that last OH group would go up. Any questions on that right there? This would be OH, and that would be our beta. So that is the only difference, and they usually will tell you which one you should draw. Any questions on that there?